Buenas tardes por venir a la última sesión. Ha sido 2 días muy largos. You can translate at the same time you wanted. Okay, it's okay. Okay. La última sesión está pensado en hablar un poco más acerca de la parte de la importancia de lo que es selectividad y sensibilidad, y enfocada un poco más a la parte ambiental y con algunos ejemplos de calidad del aire. Es una plática, pues, como relativamente corta, 30, 40 minutos. Sorry. Y después de ello, pues, clausuraremos aquí el evento. Nos acompaña el doctor José Luis González de la Facultad de Química. Y con eso daremos, pues, terminado este evento de cromatografía de gases bidimensional. Entonces, pues, les agradecemos su presencia. Phil, all yours. Last talk.
Okay. Well, thanks again, Omar. And again, nice to be here in Mexico. First trip. So you come straight to where it happens, Mexico City. Yes. My brief, as Omar has said, is to talk about higher separation quality in atmospheric sciences. I'm not an atmospherics chemist. What I can do is show you some methods that we have developed that are useful in all areas of chemical analysis, including atmospheric analysis. So a few applications are on general characteristics of this new method, which is going to be explained soon, which is comprehensive two-dimensional gas chromatography. It's an excellent technique for profiling, for discovering new compounds, for profiling samples, for comparing one sample with another sample with another sample, and seeing the fine details of the chemical changes that are happening in time or in different sample sources. So as I talk, if you're interested in this area from an atmospheric viewpoint, please think about what you do now if you're doing VOC analysis and how you could need higher separation, improved sensitivity, improved selectivity. It's common that everyone seeks to have better analysis. It's also common that many people say, I can't measure as many compounds as I think I have in my sample. Maybe you can see tiny peaks and you wish that they were better, improved. Maybe you can see, you know that you have a lot of noise in your sample, a lot of baseline problems, and would like to know how you can improve the analysis. So with that, I'd like to introduce the first part, which is about how we do this new analysis, comprehensive two-dimensional gas chromatography. So that's my comment. And this is on behalf of LICO, some gentlemen here from LICO. LICO provide an instrument that can do this.
Recording in progress.
Thank you. And you know where this is from. You know where this is from. This is my university, is what they call a group of 8 university. We have about 32 universities in Australia, but there are 8 which are the premier research intensive universities. Everyone else wants to do research, but the group of 8, we would say, is the premier research institutes. And whoops, this is, okay, flag of Australia, flag of Victoria, and if we put Mexico, then I think I should put Australia. Okay. So the technique of GC, and I'll say GC by GC, or comprehensive two-dimensional gas chromatography. I'll use those 2 phrases. because to make this comprehensive and to do complete analysis, we use two columns serially connected. That means connected in series. We have between those two columns a modulator. My modulator is that I've used in the past is rather simple. It's based on cryogenic. And to explain what this means, this modulator at this location is cooled. So even in a hot gas chromatography oven, this system, this modulator, is cooled, in my case, by liquid CO2. We can get to about minus 50 degrees or so. And in a hot oven, which could be anywhere from 50 to 250 or 300 degrees C, the modulator, as a cool system, can collect compounds and trap them. Now, many people in atmospheric chemistry and atmospheric science will know very well about trapping compounds. You can trap compounds in cartridges. You can trap compounds cryogenically. The important thing about this is that by trapping compounds, you can increase their sensitivity or their abundance or their concentration, whichever way you wish to look at this. So this system is cool, and any compounds that come from here through the column into this position will stop. They'll focus. This device, in my case, moves towards the incoming column flow, and it releases the compounds by heating up the column. So as the cool system goes to this point, the compounds that are collected are exposed to the heat of the oven, and then they move. When they move at this point, they then enter the second column, and the whole idea is to increase separation power. So you have compounds in the first column that are not resolved or potentially not resolved. Our aim at the end is to resolve the compounds one from another so that we have pure individual compounds, ideally, that you can then measure by mass spectrometry, which is the most common way of doing it. You can do it by flame ionization detection, which won't give you mass information, but it will give you the molecular identity if you have a standard. So it's about standards and using mass spectrometry and getting better separation and increasing the sensitivity of the analysis. So how do we do this? Well, first of all, we have to consider that the two columns should have different polarity. So if we have a non-polar column here, we will have a polar column in this dimension. Or a polar column here, we will have a non-polar column in this dimension. We call this, if you like, orthogonality. Because if two compounds are not resolved on a non-polar column, they still won't be resolved on another non-polar column. So you have to change the nature of the column in order to separate. But it doesn't matter which way you do it, non-polar, polar, or polar, non-polar. In this case, if we look at this as one compound or one peak that comes from this position, or this through this column, so this has already traveled through the first column, and maybe you get one peak and another, and another, and another. This will just be one of those to use as an example. But if I look at this, and I know that the peak shape should be Gaussian or a normal peak shape, then I look at this and I think that it doesn't look exactly Gaussian. So I think maybe there are other components in that peak, but I don't know how many. And if I don't know how many, what you would do normally is this would go into a detector, and then you would have to say, how can my detector tell me how many compounds I have? If one compound is small and the other one is very, very large, maybe I cannot see that other compound at all. But maybe it's a very important compound that I'm studying in order to know something about the sample, whether it be in drugs, in a perfume, or in atmospherics. So in this case, the modulator here will move back and forward. So as we see, this will be collected sharp. This part will then be collected as a very sharp pulse. And here, and here, and here. So in the end, this total profile will consist of a sharp peak, sharp peak, sharp peak, and a sharp peak. Because for 1 second or 2 seconds, we have focused. Then we focus the next part. So if I show you this, then this peak will look something like this. And you might say, this is not very good, because if there are 2 compounds here, it looks like all I've done is made it sharp 2 peaks. I don't know what's there. But of course, what happens is this moves through the column, is focused, then this moves through the second column. This is where the magic happens, because I want this peak to be resolved. And then this peak will enter the second column, because the carrier gas pushes it through. This peak, then this peak, they will progressively enter the second column. I now want this component to be separated. How many components are in there? I don't know yet. Until the second column, I don't know. So one of the important factors is that I get an increase in signal response. If this band here is 3 seconds wide and I make it infinitely sharp, it will be infinitely tall. Of course, I can't make something infinitely sharp. Let's say I make it 0.1 of a second, 0.1 of a second. So 3 seconds becoming 0.1 of a second is 30 times taller, because I squeeze that into a very sharp peak. And this is a real increase in sensitivity. For many years, chromatologists have said, I want more separation. I want more sensitivity. This is a way to do it. And we can make detectors more sensitive. We can do all these other things. And sometimes we forget that we need to think of how our chromatography can also give us that advantage. So now we see that this component has been resolved here. Now that means small peak and a tiny peak. This component, a peak and another peak. This one peak and another peak. But what's happened is within this, I should have one compound, but I could have another compound. I could have another compound. But because each pulse is expanded and resolved into multiple components, I can then plot one of the compounds, as shown here. Then here I have another compound there. And so I now know that this peak consisted of 2 components, modulated into 2 separate profiles or 2 separate individual packets of peaks. So I still get that profile for one compound, and I'll get the profile for the other compound. And the important thing here is that I have space. And so that space between two of the same components, I can fit 1, 2, 3, 4, 5, maybe 6 more peaks. So I can see the profile of one and another and another and another. So if another compound was there, I could see one profile, another profile, maybe I had another one there, maybe another one here, and I can see all of these that fit together within this one band, one peak. In the end, we present this as the peak that comes through the first column resolved into 1, 2, 3, 4, or however many compounds are resolved in that second dimension. So in this case, if I go back, here I have one peak which elutes at a certain retention time after I modulate. Okay, so this and this and this component all are located in this peak. This one would be another peak. This one would be a third peak. Now, normally what happens is if the compounds elute from here to here under very fast conditions, the temperature doesn't change much. So this should be a narrow peak, slightly broader and slightly broader and slightly broader, because in the second dimension, the retention increases a bit more, increases a bit more. So the first peak here will be a certain width, a slightly broader and slightly broader. So sometimes we look at this and we will know that the order of peaks here is going narrow to wider to wider. But sometimes if a compound elutes too late, that means it elutes after we pulse the modulator. And if instead of taking 3 seconds to come out, let's say it takes 5 seconds, that means the peak should be even wider. And so if we see a peak, if we see a peak here, which is too wide, then we say, maybe this peak should be eluting later. We call this wraparound. So we know what causes this. But so we can interrogate this. And if a peak is unusual because it's too wide, we think, maybe this should be within the one modulation pulse. So we can do some interpretation. So unresolved, giving resolved. Okay, we've achieved that resolution performance in complex samples, even simple mixtures. You know, sometimes simple mixtures still need something like this because you can get the advantage also of sensitivity. So that's good. And I call this GC by GC, making order from chaos. And I do this as an example of taking a small headspace sample of now coffee, and here it is. This is coffee. In one-dimensional GC, you'd get something like this. And if you count up the peaks, you might say, oh, I see 100 peaks. Isn't that wonderful? Well, it's good. But if you can see here, 250 peaks, you must say, why am I missing all this information? What am I missing? Why am I missing it? Then you have to interpret this as, what can this do for your samples? Not only this, but I could separate up to maybe 8,000 peaks in this space as a maximum. But if you look at this, I have got a pure peak and a pure peak and a pure peak. I've got a pure peak and there, and there, and there, and there. All of these peaks don't have interferences. Whereas if I take this peak here, that looked like one peak. And one-dimensional GC, this looks like one peak. This looks like one peak, but really it's 1, 2, 3, 4, 5, 6 peaks. How does your mass spectrometer know it's 6 peaks? You can try deconvolution, but if one peak is 1,000 times a small peak, and if that small peak is very important to you, and it's not pure, then you have a problem in interpretation. But I can have a very big peak here, like this one, resolved from something which is small there. The big peak doesn't matter anymore. I've resolved it. I can use mass spectrometry to confirm the identification of it. And maybe it's important, and I can do something with that to understand my sample. So it's not just the big peaks that are important. It can be the small peaks. If we have a pesticide, if we are eating a fruit, and someone says, this fruit has a lot of flavor compounds in, they're very strong, the flavor compounds are wonderful because they give us the flavor. But there's pesticide on that apple, but it's okay, it's only small. Eat the apple. You can eat the pesticide because it's only small. Would you say, I don't want to eat the apple? Even if the pesticide is small, because it may still be too high. And if the flavor compounds are very, very high, you're not worried about the flavor. Oh, yes, you like the flavor compounds, but you don't worry about them for health. You worry about the small peaks because they are the ones that potentially could be a problem. So that's important. So the clean mass spectrometry, the extra sensitivity, the selectivity, and the separation is the key to what we're talking about here. Okay. So now we talk about the sensitivity, the separation, the structure. Now, we've already seen separation. No problem. We've got that. Tick. We've ticked the box on separation. Sensitivity. So if we compare this, we can see that one-dimensional GC, and these happen to be steroids, and some people have seen this slide before. This is a one-dimensional analysis of some steroids. And if you look at this, some people would say, well, okay, the sample is a bit small, but we've got some good separation. But have you? Now, if I look at this, I see the peak is a bit broader. Do I ignore that? Or should I look at it and say, why? Is there something else there? Or in a case like this, it looks narrow, but I don't know if there's another compound there. If I do GC by GC, I have injected 2.5 times smaller sample. So this one should be up here. So let's have a look at this peak. This peak is small. Oh, let's say this one. Most people would say, oh, I don't worry about this because it's almost detection limit. But with comprehensive two-dimensional GC, it's here, it's there. Now, 2.5 times bigger, this peak would be 2, okay, it'd be up there. So instead of this, it'll be up there. Would you now say, oh, I don't worry about that. It's only 25 times the signal to noise ratio. No, now it's important. It doesn't have to be important for you to know, to be of concern in the sample, because you don't know what's important, or maybe you do know what's important, but you can measure it. And if you can measure it, then you can say, let me now do some further analysis. Let me see if in the sample this is important. If I know all the peaks that potentially are in my sample and could be important, then I can do some further interpretation and find out if it's important. Okay, so we've now got excellent sensitivity. The noise of the detector, you see here and here, is about the same. So I haven't increased my noise by doing this process, but I've increased the signal. Very important. So GC by GC offers better sensitivity. But if we look at this, and I've got the label 6 and 7, because in here, it's a bit of a trick. There are two components. So here we have two components. Here, I don't know why I've arrowed that one. Here, okay, we've got two components there again. And let's have a look at 6 and 7. But before that, let's reinforce the sensitivity aspect. This is a TOF MS analysis, and you've got a peak here, which is there. Now, in a chromatogram with peaks and peaks and peaks and peaks all over the place, this is only a very tiny part. This is only 20 seconds in an analysis which might be 40 minutes or something like this. So when you look at the chromatogram, you won't see that. You won't see it because it will look like a flat baseline, because most of the peaks are not. Now, this is expanded. Most of the peaks that you see over here might be a really big peak and a very big peak over there, and this one. And you'll say, oh, no peak there, nothing to worry about. But is there? When you do comprehensive two-dimensional GC, all of a sudden you see a peak there and there and there and there. And then you say, oh, I didn't know there was a peak there, but there is. And if you look at the ratio of the ions, this one is 270, 270, 270, 270, 270. The next one, the blue, is 345. Okay, 345, 345, 345, 345. The ratio is constant for the first pulse, the second, the third, and the fourth, which means by library matching, I hope this, and this show 4 pulses, 4 modulations, all with the same identification, because you can library match each one of these. And if it is, then you are very happy and you go on to the next peak. But you can see here from something that you had no knowledge about to something that you are certain is there and you need to consider it. It's part of the analysis. You're not ignoring it, and it means something to you. So sensitivity improvement again. And again, that was spheroids as the previous sample. Another comparison, GC by GC offers better separation. Look at peak 6 and 7. Well, in this case, remember peak 6 and 7, this was what it looked like, and we thought the peak shape didn't look symmetrical. This looked symmetrical, but this one didn't look symmetrical. But sometimes an analyst is very busy. They won't look at this. They won't look at this and say, I think there are 2 peaks there, because they're interpreting one result, they're injecting the next sample and the next sample. They don't look at every part, every part, every part. And they probably just assume that, okay, let's accept the report. The report tells me it thought it was 1 peak. I'll just go on. But now it comprises 2 peaks. Now the hash, there's a component there, and there's a component star, a bigger component. So this one is a bigger component with a smaller component there. And that's why the peak seems to be a little bit fat on one side, so a bit broader, and then comes down, because you've got a leading edge overlap. And this is easy because you've got 2 clear peaks, which in GC by GC, the 2-dimensional plot, you'll have a peak there and a peak there with first dimension retention, second dimension retention. first and second dimension retention, individual separate peaks with a GCMS result. So that's now all done. So comprises two peaks are seen here. But this is one peak. It's symmetrical, and the modulations show that it is a single peak. So I don't see, there's no other sort of separated component. Happy with that. And we can consider the value of reproducibility of the 2D space for identification, because this is now comparing one sample with another sample, And this can go for, be for any sample comparison that you want. Again, drugs, I show an example here for olive oil, coffee, atmospheric samples that you've collected for a long time. You now want to do the best possible analysis you can do. So aspirational is, once we identify a peak, we hope that its position means that it's the same compound from one analysis to the next. If it's the same sort of sample, it should be. So if you've collected atmospheric samples, for instance, and there's a time variation, say during the day, chances are this sample and the next one and the next one will be similar. And if it's similar, then the 2D plot will have a similar composition. Some may be larger and smaller during the day. And if that's the case, then you just process this in your data interpretation as necessary. We can use filters of peak position, like a retention index and mass spec, to provide improved certainty. Now let's show you this one. This is one-dimensional GC of a Hoya Blanca, and I don't know where that name comes from. It could be Spanish. Do you recognize this? These are olive oil volatiles in one-dimensional GCMS. So we just sample in the headspace into the GCGC, and didn't need to go there. So this is the one-dimensional GC of Corentina, Barnia, etc. Peak 11, peak 11, peak 11. We know that retention time should be consistent from one run to the next, And we know that 7 and 8, 7 and 8, 7 and 8 should be about the same in each of those. And that 3, 4, 5, 6 are clusters here. Now here, 5 is a bit bigger than there. So the ratio is a bit different, which means that you've got a comparison of, in this case, the flavor profile, the aroma profile of these samples. But there's lots of little peaks here that may or may not be important in, say, characterizing or classifying these samples. What is the major difference in these that help you classify the samples? Well, if we do comprehensive two-dimensional GC, we have much more information on which to base that classification. For instance, we might be able to say which olive oil samples are related in terms of parentage. Is the parent of this one, is that a hybrid of two parents that have some relationship, or is it completely different? I don't know, maybe this could be done. In this case, we add some internal standards here and here, here and here, here and here. And the important thing is that they are almost always exactly the same position. Hopefully the next day, they're also in the same position, and the next day. But if not, then you can say, oh, there's a bit of a change. So I can adjust my chromatogram to compare one day with the next And if I see these components, 1, 2, 3, 4, 5, or something, 1, 2, 3, 4, 1, 2, the position is always the same. And I can say that, well, I think I've got 3 peaks there, but I've got 4 peaks there. Ah, that one's missing. from here. And so once you identify what that peak is, you don't have to go through mass spectrometry and all the rest of it for the sample here. It's going to be the same peak. And so you can say same retention, first and second dimension, same position. You can write the name of the compound. You could be blind and write the name of the compound without mass spectrometry. But you need mass spectrometry as a confirmation. And you can do the same here and the same with that cluster. And so there's probably one peak that you saw in one dimension, but now you see 4 or 5. There's never a problem with having too many peaks. There is a problem with having not enough peaks. Not enough peaks means you miss information. More peaks means you can ignore some if you prove that you don't need to know them. This is coffee, Arabica and Robusta. You see the four peaks there, 1, 2, 3, 4, down here, 1, 2, 3, 4. I bet that this peak here is the same as that peak there. In one-dimensional GC, the same peak position doesn't necessarily mean it's the same component, because if they're overlapping, you don't know the relative amounts. But in this technique, because you've got 2 separate dimensions, if you like, you've got a profile which says, I've got a correlation with the chemical structure. It's almost absolutely sure that that is the same as that. And you can see the same thing here. That will be the same as that. And down here as well. So this should simplify the whole process in ways that you can't do with one-dimensional GC. One-dimensional GCMS, you have to go through every peak every time. With this, once you classify the whole space, you can say, oh, same position, probably same compound. You just do a check. Oh, here's a peak that's at a different position. Oh, I better go and check that. And then you write the identification. This is something that comes from some, research in my lab done by a visitor. His name was Alistair Lewis. He came to my laboratory many, many years ago. He was, in fact, my first ever visitor into my laboratory as a visiting scientist. Since then, I've had about 75 visitors in my laboratory. He was the first. He produced some information and publication in my laboratory, which is published in Nature. So my first publication on this technique was in Nature. And since then, we publish in less quality. That is sad, but I'm happy with this. And what he did was he brought some equipment to my laboratory. He put a snorkel, or if you like, outside the window in my laboratory. It brought in samples from outside, air from outside in Melbourne, processed them, pushed them into the GC by GC, but we used FID at that time. I had no mass spec. And this is the one-dimensional GC, and this is the comprehensive two-dimensional GC. And the important thing about this is that one of his supervisors, which was Michael Pilling, Leeds University, put some numbers into a model. And he found that the model didn't explain, the model based on this didn't explain the results in this. So he was able to say, I need to develop a new model. I think they call it a box model or something, a new model to explain all the additional information I get from the molecular separations. So when they did that, they found that they could improve the model of atmospheric ozone generation, because sunlight on these pollutants can cause ozone and other things. So that was a win for us and a win for Ali, because he's now a senior professor at the University of York, leading about 100 scientists and he's got multiple appointments all over the place. When he went back to he was at Leeds at the time. When he went back to Leeds, but very soon after that, he got to York. The university, when they saw this, they said, "How can we help you? Do you need resources to further this project? How can we help you?" Unfortunately, my university, which was a different one to mine at the moment, said, "Oh, a paper in Nature, it's only a communication. It doesn't count." Now, there's an experience there. But you can see further information here. So further details, these further distribution of the 1, 2, and so the bands here tell us something about these. There's aliphatics and aromatics and all these other sorts of things. And they said that the oxygenase species were observed to during a period of 2:30 to 5 o'clock, consistent with the formation of photochemical processes rather than primary emission. Okay, that's good for the interpretation. I don't know what it's here that tells them that, because I'm not an atmospheric scientist. But this expansion, again, means you can dig into the detail. You can't do that with one dimension because you end up with grass. But here you can, because you've got meaningful separations of meaningful compounds. And if you look at this, these compounds will be the I suspect they're probably alkanes, but it says elution of aromatic compound. But you see some minor components there that you wouldn't see here. And those minor components have names, have abundances, and all the rest. So that's important. And this is another example of atmospheric. So I'll just show this. It's just to show that you can get some trends in the elution patterns, which mean you've got common compound classes and things like this. So a lot you can do with identification through this process. Okay. Recently, Ali just sent me this. It's one-dimensional GC, but there's lots of peak overlaps, but it's only in a short period of time, a short time span, because he's doing very high elution or fast elution of these compounds. And he's just talking about advantage of GCMS over PTRMS in order to get speciation, because you don't get speciation with PTRMS. You can now see CFCs, HFCs, formaldehyde, etc. in this, and you can actually do GC by GC on these compounds, but you've got to be careful with the small molecular mass compounds. We don't always just work with small mass compounds. We can do, of course, most often higher mass compounds. Okay, very fast incense analysis. In this case, we are looking at burning incense using GC by GC and POF-MS or electron capture detector or NPD, etc. And this is the way we did it. Very simple. We had a joss stick there. You burn the joss stick, and smoke goes through here, and you can put the fiber of the SPME into the smoke. The fiber turns black after a while. Or like this, we would put the fiber on the side and sample the side smoke, not the aroma, if you like, not directly in the smoke. And so the two different approaches, direct sampling or side sampling. And Tibetans are red joss, brown, smokeless, medicine herb. Medicine herb. If you smell the smoke from this, you don't call it medicine. You should call it toxic smell or something. But these are supposed to smell nice, lotus scented, orchis scented. Yes, but once you burn it, not so good. So we would powder the joss stick. So you make a powder, you measure the headspace, you get all the essential oils, no combustion products. But here, it's the smoke. And not only do you see remnants of those components in here somewhere, of course, you know where they are. You just have a mask that applies them to the next sample, and you can remove all of the original compounds and look at all the smoke-generated compounds. And these compounds are furans and pyrans. They contain nitrogen, phenols, polyaromatic hydrocarbons, benzene, naphthalene, etc. Oh, plus some essential oils. You're not worried about those. But if you're in a temple in Hong Kong and you're breathing all this in, makes you wonder how good it is for your health. Red Tibetan powder, again, the initial, sorry for the dullness, the initial powder versus the smoke. And it looks like a lot of these are combusted, but there will be some residuals. But look at all the compounds that are produced, small molecular weight molecules that are generated by the smoke. This is lotus powder. Oh, sorry, lotus, red, brown, and medicine. That's incense powder and the smoke. You can see the difference. Powder and smoke. All of these ones generate new compounds, a lot new compounds there. But you can profile these. If you want to do a study on generation of smoke, it doesn't have to be joustic. It can be smoke from down the local road in terms of pollutants emitted from vehicle sources and things like that. And here you see benzofuran, biphenylene, phenanthrene, down to some original compounds that were in the joustic. Okay, comments, we can subtract the background from the sample results. Incense material, powder, essential oils. Combustion products and smoke comprise many and potential environmental pollutants. Some are ECD active, which means they're probably nitrogen containing, etc. Many PAHs and substituted pHs, nitrated, etc. produced. The high resolution data in GC by GC tells you the speciation, it tells you the sensitivity, improved by the sensitivity for this analysis. Okay, so that's my presentation finished. I think I've given you a hint about how you can apply this technique, why it's important. If you're doing VOC analysis and you have problems with sensitivity, with separation power, this is certainly a technique to consider. It's one now in our, we call it our, it's a bucket list, but it's in our toolbox of a technique which really these days is far too important to ignore, because other people will be using this technique, and it's important to get in early to establish experience, to get researchers involved in it, maybe some students if you have a PhD program, be part of the community, be part of the research that appears in this, because the earlier you do it, the better it is, because other people would be doing it. So thank you.
Estamos conectados en Zoom para que muchas gracias. Well, thank you so much. Sorry? No aquí, no sé si es la última vez. It's a small room. Yep, but as they are, yeah, they are recording on Zoom, so just confirm if is it open. Okay, no. Puedes hablar también ahí por el... Oh, sorry, you don't mind. Thank you so much. No, it's my turn. Muchas gracias a todos por su atención. En caso, bueno, vamos a tener este periodo de 50 minutos para preguntas y respuestas. Entonces, si alguno de ustedes quiere hacer alguna pregunta, por favor me comentan para que hagamos pasar el micrófono, porque se está transmitiendo. Entonces, si quieren hacer la pregunta en español, la traducimos. Si la quieren hacer en inglés, bienvenidos, ¿no? Entonces, ¿tenemos ya alguna pregunta puesta? Menos de 50, disculpen. Yo iba con horario de Australia. Ok. Yo tengo un par de preguntas para abrir, ¿no? Digo, la serie de comentarios.
He has some questions just to open the
Voy a hablar en
question and
español.
answer section.
O sea, nos queda claro que es súper importante tener durante el análisis
That it's important for us to, during the analysis,
evitar falsos positivos. Esto quiere decir tener una identificación certera. Y por lo tanto, al tener la identificación del compuesto objetivo o de interés confirmado, pues entonces tendríamos también un análisis cuantitativo certero. La pregunta es, ¿qué pasa cuando no se tiene en cuenta estas dos variables en mezclas complejas sobre políticas públicas?
what happens when we don't have those two variables understood for moving policies?
Is that a question or a comment? I can answer either way. Either way. I agree. No. Obviously, information is important. We're driven by information. If we need to understand our samples, we should try to be as comprehensive as possible in interpreting what is present in the sample. If we don't know what's in the sample, we don't know what's most important. We might be able to identify a few things, but how do we know that the simple things or the things we can analyze are the most important? If we don't know the most important, and this is what I said about pesticides. If you are analyzing fruit and you're analyzing all the nice compounds, but you don't analyze the pesticides, then regulations might say, oh, this is acceptable. You can eat it. Later in the year, someone might say, oh, the analysis was wrong. You've all been eating pesticide and fungicide-laden fruit. The community will not be happy. And so you shouldn't aim to do bad analysis. You should aim to do good analysis, because good analysis with the identifications and the quantification means that you are being fairest to the public. And therefore, you know that you can rely on the food production and all the rest of it. Because we had a case on pesticide in beef sent to Japan. If the regulations in Japan and the testing of the meat meant that the pesticide level was too high, the laboratory, maybe in Australia, obviously either didn't measure for those pesticides or used the wrong method. And when the meat was sent to Japan and it's rejected, it might be, let's say it's $2 million worth of beef. Then you don't say, the Japanese won't say, it's too high, we reject it. The Australians aren't going to say, okay, shh, we'll send it to somewhere else. No, you'll have to destroy it. But that's very important. You can't afford a market to be destroyed because of that. And you can't afford people to then eat things which are going to cause problems. So regulations are very important, and you must have quality analysis to protect the community.
Y eso da origen a la segunda pregunta. Parece obvia, pero ¿cuál es tu opinión acerca de tener un buen control de calidad en las mediciones?
Quality control, people would say you can never have too much quality control, because if you have good quality control 2 years ago and you forget the quality control, then you can't say, oh, it's good because 2 years ago we had good quality control. but we didn't bother about it this year. So we actually don't have quality control. So the expenditure on quality control is the confirmation that you're doing things right. And if you show that you're doing things right, then you can't be criticized for the quality of your data. The good quality data is hand in hand with good quality control. Absolutely important.
Gracias. Bueno, a ver, yo ya pregunté, ¿ahora les toca a ustedes? Sí.
Gracias. And what is your opinion about the use of NIST library or ChemSpider library to the identification from data from TOF-MS?
Well, I think the question about being from TOF-MS isn't just TOF-MS. It's quadrupole MS. It's all sorts of mass spectrometry. Because, see, what happens is you will accept a certain match, maybe 80%. Is 80% enough? Or can you go down to 70%? I see sometimes people say 60%. Oh, that's enough. But sometimes 95% will still not be correct. You can have isomers that give you 95%, 94%, 93%. And you say, well, they're different isomers, but they're all got matches greater than 92%. And you could imagine that if that isomer was not in the library, the isomer that you have is not in the library, you'll be identifying it as the wrong isomer. Now, we published something last year with a professor from Rio de Janeiro, Embrapa, where we looked at retention indices combined with mass spectrometry, asking people to improve their confirmation of compounds, because people use retention indices incorrectly, and then they use mass spectrometry incorrectly. And we can't blame NIST, because NIST is only trying to compare two spectra where the spectra have differences. Even one day, this mass spectrometer and that one and that one and that one will have slightly different spectra. And the only good spectrum is the one that you obtain in your library, in your laboratory at that day, compared with the standard on the same day. Even then, you won't get 100%. So you've got to always be very, very skeptical and use scientific judgment about use of mass spectrometry. But of course, the authentic compound is most important. You don't always have that, and that is a real problem. So we have a problem with this when we review papers. Yeah, yes, please, because we have a mass spectrometrist.
Hi, my name is Alan Griffiths. I'm the Director of Separation Science Sales for LEAK-I. My history is engineering and mass spectrometry. What I would like to add to that, I don't know who asked the question, but I'm assuming that that question comes from a knowledge of TOF-MS. And TOF-MS many years ago was very, very different spectra to single quads. A lot of modern TOF now, due to the different ways in which the mass spectra is created, they're much, much more similar to single quads now, very, very comparable. So the latest, the newest models, you wouldn't really be able to distinguish much between the TOF and the single quad. Hope that helps.
Fórmense.
Gracias. En el mundo de los tóxicos utilizados en la industria de los plásticos, el factor de la propiedad intelectual oculta verdaderamente el universo de aditivos utilizados que atentan en contra de la salud humana y el medio ambiente.
Perdón, ¿podrías ir un poco más despacio para que le pueda ir? Gracias.
En el mundo de los tóxicos utilizados en la industria de plásticos, el factor de la propiedad intelectual oculta verdaderamente el universo de aditivos utilizados que atentan contra la salud y el medio ambiente. Con este progreso tecnológico en la caracterización de tóxicos, ¿cómo se pueden las organizaciones no gubernamentales acceder a estas tecnologías para desarrollar informes de incumbencia pública para todo el público?
Why, but I heard something about this.
Perdón, ¿a qué te refieres con propiedad intelectual?
Conocemos que hay empresas productoras de plástico que tienen sus patentes privadas. No conocemos los componentes totales de un plástico por las patentes y la propiedad intelectual de los usos comerciales de la patente.
Gracias.
Well, this is probably a question beyond my knowledge of plastics and things like this, but certainly things like migration into food is a big problem, from plastic wrap into food and things like this. Even if that's the question, and you can put plasticizers in and things like this, and maybe, as you say, also intellectual property or patents, and they don't want to tell us what they've made from that. I don't know what the problem, how to resolve that problem, if unless someone can say what they actually put in it. But if you then put the plastic into landfill and it leaches out and it goes into the water body, and then you have to measure the water quality, you'll get either surprises, but you should again be using something like a complete analysis that will give you a complete profile. But I think Alan wants to say something.
Plastics are, as you say, unique to the manufacturers. Each manufacturers have their own additives, softeners, plasticizers, etc. And it's very difficult to know specifically what's in there. Typically, the best way to do it is to be able to get the pure plastic from the individual manufacturer. Good luck. But what you can then do with that is a process, probably the best process that's known at the moment is TDPY-GCMS, GC-GCMS. So that's thermal desorption, pyrolysis, GC-GCMS. And that's by taking the sample directly, putting it into a suitable system. So there's one such as the Optic 4, where you can put it inside the liner and you very gradually heat it up to create a thermal desorption. Just to add to the complexity, you can have a cryogenic trap to trap the analytes before sending them off into the GC. You can then take it up to a higher step of thermal desorption, and then you can take it up to another step where you're actually pyrolyzing the sample. So that way you get the analytes that are added to the polymer, and then you also get the polymer itself. The problem comes when it's not in its pure form. So that's a good way to identify that particular one. And if you've got those individuals, when you have a full sample, such as an environmental sample, which has got multiple polymers in it, has got multiple other things in there as well, other environmental analytes, it's then a matter of trying to pull that whole thing together. This can be done because if you have good software, then what you can do is you can apply filters to your chromatogram. So the big chromatograms that Dr. Marriott was showing, you can apply filters to those so they only show such things as phthalates or certain polymers or the breakdowns, the monomers themselves. And so you can break it down, but it is a very, very complicated process. There are many papers out there that talk about it and discuss it. And you can certainly find more. Imperial College in London, there's a big group there. They advise the UK government on environmental samples such as microplastics in the air that you breathe in London, etc. So it can be done, but it's very complicated. There are standards that are available. They're very hard to get hold of because I think there's only one company, Frontier Labs, that makes plastic polymers as standards. The other difficulty that you have is this kind of instrumentation is extremely sensitive. It's really, really powerful. And the problem is, if the plastic is big enough for you to see, there's a pretty good chance it's too much. So you have to find a way of taking your sample, making it homogeneous, and diluting it. And for the most part, you can't dilute it with a solvent because the solvent will only dissolve some of the polymers and not all of the polymers. So one method of doing it is by diluting it with silicon dioxide, with sand. But again, that has to be a powder form. And you've obviously got to make sure that you work well with your liners because you don't want your sand to go into your chromatograph. So again, it's quite a complex process, but it can be done. No problem.
Ok, nos salimos de la complejidad. ¿Alguna otra pregunta? Última oportunidad. Ok. Dos. Wow, bien.
Thanks a lot for the presentation. And I want to ask about, in the same way of the plastics, in the pesticides, we found different compounds like emulsifiers, sulfurants, and it's possible to found in the GC by GC method, or it's not possible because are in the secret formula of the commercial pesticides. So it's possible to found this like huella, the footprint, the print.
I'm not sure. What are you looking for? You've got the pesticide, but
the emulsifiers and sulfates in the pesticides.
So
in the commercial pesticides.
Wasn't sure.
There are other aspects to the pesticide rather than the actual pesticide chemical.
Yeah.
Okay.
For example, you're talking about before with the actual process of making.
Oh, okay. So you might call the adjuvants and things like this that maybe make the pesticide compatible spray fluid or maybe aqueous systems, so that you've got surfactants and all sorts of things.
Exactly.
It makes me surprised that if a manufacturer will say, "Yeah, we got this pesticide, but we're not going to tell you what other things we've got there."
Exactly.
It doesn't seem right that they can tell you one, and they have to tell you one, but they can't tell you the other thing. But in this case, if you can apply if they're volatile and you can apply the chromatographic technique, and you can find them in the 2D plot, even if you can't identify them, you might say, well, there's something here. I have to search somehow to find out and discover what this is. And the best way to discover it is to search your mass spectrometry data, and database and things like this to see if it is known compound. But this is not easy all the time. But the best thing is, of course, to have, as you say, a fingerprint, and this is your data, and maybe even go back to the supplier and say, look, there's something else in this. We need to know what it is because we can't identify it and we think there could be a problem. Now, if you're in the regulation area, you can do that. If you're in the public laboratory, maybe you can't do that. But I think we have to put pressure on people to make sure that we know what's in there. If we are eating a food, we have ingredients, and we know that the ingredients are important because we know what we need to put in our body. That should be applied to a lot of other organizations, but I don't know whether there's an additional.
I found this again, and so you can start to build up a picture. And then, as Dr. Mary was saying, when you are trying to get information, from a manufacturer, you can go down and say, well, actually, we found this in 5 different places and we're getting quite concerned. So we need to know what this is. So you can build up a picture by using this as opposed to necessarily having to absolutely identify it, because they could probably quite likely be unique to that manufacturer.
Thanks a lot.
No problem.
Última pregunta.
Hola, buenas tardes. Yo la voy a hacer en español. Bueno, aquí en México no está regulada la parte de la identificación de plaguicidas, de pesticidas en agua y en alimentos. Me refiero a que no hay una metodología normada para seguir. Entonces, aquí lo que se quiere hacer es una metodología en donde se puedan identificar todos los plaguicidas que contemplen las normas. Sin embargo, yo recientemente pedí un permiso para utilizar una tecnología que se llama MRM, que es un triple cuadrupolo.
¿Puedes repetir la tecnología? MRM.
MRM es
Ajá.
la metodología para analizar en un triple cuadrupolo volátiles, compuestos volátiles, BTX. Pero tuve que pedir un permiso especial para poder implementarla. Ahora, lo que quisieras yo saber es yo entiendo que es más, tiene un alto poder de selectividad, pero volviendo a todo lo que es control de calidad, ¿es rentable también hacerlo con usted, bueno, en esta manera con GC by GC?
Provided the pesticides are volatile, yes, I think this is an excellent way to go. And we did see, and I showed some data where you can get degradation of pesticides producing degradation products. It really surprises me that that all manufacturers, and I think all manufacturers who make pesticides, first of all, they have to do the chemical analysis. They have to prove that it's safe. They will also have done, I'm sure of it, MSMS, and MRMs. So that information is somewhere. Maybe it's not always available in the literature, which really surprised me, because there are many groups around the world who specifically always do MRMs for pesticide analysis day after day after day. And that is available. It should be available somewhere. I don't think Mexico will have an invention of a new pesticide. It'll come from Monsanto. It'll come from somewhere else that has done some fundamental studies. They know the degradation and the breakdown products and things like this. That should be available. Getting it in your hands might be difficult. I don't know how to. Maybe there are organisations who deal with this at an industry level. Could be, but one thing I will say is that, and I would say yes, GC by GC should be a way to go. I was talking to someone not long ago, and they were dealing with what we call legacy pesticides. Legacy pesticides that maybe aren't used anymore, but they are often found in river sediment. And over time, they leach out. And so a research or a group, an industry group, was interested in looking at what those legacy pesticides were. And he insisted that they use GC by GC, TOFMS, to profile all of those sediments. And they said, no, we just want to measure those that we know are there, we think are there, and profile them by MSMS. And he said, but you're probably missing many things. Why do you analyze something that you're probably going to be missing when we've got a technique that we know works and can profile and can store all this data for posterity over a long period of time? We can measure it and we can compare it with legacy pesticides from other places, but you must have the full GC by GC profile, and don't hide things. See everything there. And I wish you luck in trying to find that information, but I think it should be available somewhere. Do you know if there's an organization that...
I would step slightly aside from that. One thing I just quickly pop in, don't bother doing triple quad with GCGC. That's probably a bad idea. GCGC is not good enough. Probably the most advanced area in the world in this kind of analysis is probably Europe. They're very strict. They have a thing called the Water Framework Directive, where WFD, where all the waterways of Europe have to reach a certain standard. And there is a huge list of pesticides, of pharmaceuticals, et cetera, persistent organic pollutants, et cetera, and this huge list, and the list grows. Every year, more come out, there is more analysis done, et cetera, and there is a huge move within the community towards TOF, and there's a great interest in GCGC. And the reason for that is because there's this constant change, they need to have the data previously to what they have now. Now, you don't need MRM if you do TOF, because with TOF, you just do a direct analysis. So you can just see it straight away. Not quite as simple as straight away, but you compare it with NIST libraries, et cetera. And now the latest TOFs that we produce have got the sensitivity of a triple quad. So you don't need to use a triple quad to get the sensitivity. That's not necessary anymore. So you can certainly use GCGC. To do that, you would need a TOF to get your best results. You would want to use a TOF. And there's many examples of it coming out of Europe at the moment. The most recent one I'm aware of is the Natural Resources Wales. They just they've got a very big lab. They cover the whole of the country of Wales, look after all of their water supplies. They did a huge tender, very open tender, to find out what was the best. So some companies put forward high resolution mass spectrometry. Some people put forward GCGC, et cetera. And they chose a GCGC TOF-MS as their final result. And I'm sure they'd be open to discuss it with you if you wanted to.
Excelente. Ok, pues démosle un fuerte aplauso, por favor. Lo que preparamos de la mesa para que nos haga favor el doctor José Luis de clausurar el evento, presentar, le vamos a entregar esta constancia a Phil. Yo sin... I will give you, for you. Thank you again. And, por favor, una fotografía para el doctor Marriott recibiendo su diploma. Thank you. Thanks for coming. Ok, si me hacen favor. Unos minutitos para la clausura. Gracias, Bárbara. Muy amable. Phil. Phil, Alan. Tiago. Salud. Jorge. No me confunda. Sí. Por favor. Nos va a hacer el favor de clausurar el evento el doctor José Luis González Chávez, él es profesor de carrera titular C de la Facultad de Química y coordinador del Departamento de Química Analítica de aquí de la Universidad Nacional y quien ha sido una pieza clave para el desarrollo del evento. Gracias a él estuvimos en la Facultad de Química, en el Auditorio B y todas las facilidades las recibimos gracias al doctor. Muchas gracias. José Luis. Te voy a pedir que nos dirijas unas palabras.
Sí, bueno. Muchas gracias. No me había advertido nada, Omar. Sí. Pero bueno, antes que nada, agradecer al doctor Philip Marriott su excelente presentación. No es mi área de especialidad dentro de la química analítica, yo soy químico analítico, soy más electroquímico, sin embargo, no pude estar en todas las sesiones por juntas y clases, en fin, pero los momentos que estuve fue sumamente claro, entonces supongo que para los especialistas de verdad que fue todavía muchísimo más claro el potencial que muestra esta posibilidad. Esta última pregunta estaba así tentado a comentar algo. Tengo experiencia en lo de armas químicas. Soy inspector de armas químicas de Naciones Unidas y estuve tanto en el Consejo de Seguridad como en Holanda, en La Haya. Y estas cuestiones de los análisis, los laboratorios acreditados para el análisis de los tóxicos químicos, que lo nombró ayer en su presentación, cómo determinamos la confiabilidad, control de calidad, cuántos picos son necesarios en la espectrometría de masas para considerar que hay una probabilidad de que sea, en fin, hay toda una historia detrás de esto, los pesticidas que están muy relacionados con las armas químicas, ¿no? ¿Sí? Pero bueno, agradecer al doctor Philip Marriott, agradecer al ECO, como nos decían ayer, estas pláticas son gratis para todos nosotros. Gracias al ECO, de verdad es una excelente oportunidad. Ya se fueron ahorita algunas gentes, pero teníamos auditorio lleno aquí, teníamos auditorio lleno en la Facultad de Química los 2 días. Habla de la importancia, no solo porque haya sido gratuito para nosotros, pero habla de la importancia de estos métodos de análisis. Agradecer a Omar, me dice que me deben muchas cosas a mí, ¿no es cierto? Omar me invitó a, pues ni siquiera coorganizar esto, fue más una cuestión de tipo administrativa en la Facultad de Química, con algunos detalles, hay que ver las cuestiones con gente de sindicato, y ya saben ustedes que cuando hay sindicato de por medio, pues hay muchos detallitos, ¿no? Pero bueno, sobre todo agradecer a todos ustedes por su participación en este evento, que de verdad te agradezco mucho, Omar. Nos conocemos hace algunos años, ¿sí? Y esperemos que la colaboración con el Departamento de Química Analítica, sobre todo la gente que se dedica más a esta área, pues crezca mucho más, ¿sí? Muchas gracias a todos. No sé creo que no se llama ni seminario, ni coloquio, ni nunca encontré un nombre para
Hay que
esta
encontrar el nuevo
jornada.
concepto como
Sí.
modulation ratio. Aquí hay que encontrar el concepto.
Sí. Muchas gracias por toda su participación y declaro concluido este evento.
Muchas
Gracias.
No sé si alguien quiera decir algunas palabras, cierre.
Just we're closing. Okay. Luego, algunos ya les agradecí cuando están en la participación en el otro auditorio. Esto es lo que espero que sea el primero de varios eventos que vamos a empezar a realizar acá en México. Elegimos este lugar, la UNAM, por la colaboración del doctor Omar, que nos ha prestado para empezar a divulgar el nombre del ECO y la tecnología de Pegasus, que presta y ayuda a realizar análisis bidimensional. No está tan conocido en la República Mexicana. Es algo que queremos cambiar colocando o promoviendo más este tipo de evento. Siempre van a ser gratuitos, eso no es problema, pero la idea es que ustedes conozcan otras opciones que existen en el mercado, otros fabricantes de lo que ya están usando y que nuestros equipos puedan llegar a ser un complemento o una alternativa a lo que ya han conocido en su manera de hacer su análisis. Entonces, de nuevo les agradezco esta oportunidad, tanto a la UNAM, tanto al doctor Amador, al doctor que nos está prestando el auditorio, que ha sido un evento estos últimos 2 días fenomenal. Todo ha sido más de lo que esperábamos. Y gracias a ustedes por el interés que nos han mostrado, la participación, las buenas preguntas y más que todo su atención. Muchas gracias.
Gracias.
I'm going to talk again. First of all, thank you very much for facilitating the function here at the university, making the facilities available. That was very generous of you and generous of the university, so I'd like to thank them. I'd like to thank LECO for putting on the show, Omar, my good friend, haven't seen for a long time, for again putting together the program, putting together the many bits and pieces of the program that has worked so well. I would like to thank the audience for for always, I think, staying awake, because frankly, if I listen to myself, I go to sleep. But we had nice questions, thoughtful questions, and I'm sure that many people could have also asked additional questions that they thought maybe that they just didn't get to write down. But thank you for your participation, and thank you again for your questions and being interested, particularly in a new technology, which is, I think, very important. So I hope that in future, I hear that there are systems, additional systems in Mexico here, which means that LECO are going to be people are providing you with those facilities. Good for LECO, but also good for you, because this is the power and as the information that is there is so very important. And I think you can see that. So I wish you well in getting budgets. So again, thank you very much.
Gracias. Okay. That's it. Gracias.